All right, let's talk about one of those reactions that pops up everywhere, from your exams to huge industrial processes, the Reimer-Tiemann reaction. Now, I know what you're thinking, another name reaction to memorize, right? But stick with me because this one is less about just memorizing a formula and more about appreciating a really clever tool. Think of it like a chemist's version of a surgical scalpel. So how exactly does this thing work? Let's dive in.
Okay, so let's put you in the driver's seat. Imagine you're a molecular architect. You've got this beautiful molecule, phenol, you know the one, that classic ring structure, and your job is to add just one, new piece to it. But here's the catch. It has to go in exactly the right spot. You can't just slap it on anywhere. How do you pull off that kind of surgical precision without wrecking the whole molecule? Well, that's the puzzle we're going to solve today.
So, what's the answer to our little architectural problem? You guessed it, it's the Reimer-Tiemann reaction. This is the elegant, purpose-built solution we've been looking for.
Okay, so what is it exactly? The textbook definition calls it a formulation reaction. Big word, I know, but it's actually super simple. All it means is we're adding a formyl group, that's a CHO group, which you probably know as an aldehyde. But here's the really cool part. This reaction is picky. It doesn't just add that group randomly. It has a favorite spot, the ortho position. That's the carbon right next door to the OH group that's already on the phenol.
So here's what it looks like on paper. This is the whole recipe. You take your phenol, you mix in some chloroform, and a good strong base like sodium hydroxide, and voila, out comes our main product, salicylaldehyde. You can see it right there. We've taken our starting material and perfectly stitched on that aldehyde group, right in that ortho position. Mission accomplished.
All right, let's meet the key players in this little chemical drama. First up, our substrate. The molecule getting the makeover is phenol. Then we have our reagents, the real workhorses, chloroform and sodium hydroxide. Think of them as the tools for the job. And finally, the grand result, our main product, is salicylaldehyde. If you can just remember who does what, you've basically got the plot figured out.
Okay, so we know what happens, but the real magic is in the how. How does this tool actually perform this molecular surgery? Well, we're about to pop the hood and look at the engine of this reaction, the mechanism. This is where things get really interesting.
So the whole thing really comes down to three main steps. You ready? First, we have to generate the scalpel. The strong base, our NaOH, literally yanks a proton and then a chlorine off of the chloroform. What's left is this wild, super reactive intermediate called dichlorocarbene. That's our scalpel. Step 2, the precise cut. This carbene is desperate for electrons, and the phenol ring is full of them, so it attacks, zeroing in on that ortho position. And finally, step 3, the final polish. A little bit of water comes in to clean things up in a process called hydrolysis, and that converts the intermediate into our final, beautiful aldehyde group. Done.
Look, if there is one thing you absolutely have to remember about the mechanism, for any test, for any exam, it's this: dichlorocarbene. This little guy is the key to everything. It's a super unstable, high-energy intermediate, and it's the secret weapon that drives this entire reaction. You will almost certainly be asked about it.
All right, that's the chemistry, and it's pretty neat, right? But you might be sitting there thinking, okay, cool, but why does this actually matter? Well, let's connect the dots. This isn't just a lab trick, it's a doorway to stuff we use every single day.
You see, the salicylaldehyde we make isn't usually the final destination. It's more like a launch pad. It's a critical starting material for making all sorts of things. We're talking dyes, fragrances, chemicals for farming, the list goes on. But the most famous one, the one that I guarantee you've tasted, it's the key to making vanillin.
And here's the pathway, plain and simple. You start with cheap, abundant phenol. You hit it with the Reimer-Tiemann reaction to get our salicylaldehyde. A couple more steps, and boom, you have vanillin. That's the stuff that makes your ice cream and cookies taste amazing. So yeah, the next time you taste that artificial vanilla flavor, you can give a little nod to the good old Reimer-Tiemann reaction.
Okay, let's switch gears. For everyone out there studying for a big exam, this next part is for you. We're going into rapid fire mode. These are the high-yield tips that will absolutely win your points. Pay attention, because this is the #1 mistake people make. They get the Reimer-Tiemann reaction confused with another one called Kolbe's reaction. They look similar, but they are totally different. Let's break it down. Reimer-Tiemann, you use chloroform and you get an aldehyde, salicylaldehyde. Got it? Kolbe's reaction, you use carbon dioxide and you get a carboxylic acid, salicylic acid, which is used to make aspirin. The reagents are different, the products are different. Don't fall for that trap.
All right, here's your final exam checklist. Let's do a quick rundown. What are the reagents? Chloroform and a base. Check. What's the major product? The ortho product. Why? Because of that awesome hydrogen bonding stabilization. What's the star of the show, the key intermediate? Dichlorocarbene, of course. And what about the minor product, the para one? Why is it minor? Steric hindrance. There's just not enough room. You nail these 4 points and you are golden.
So, if you had to explain this whole thing in one breath, what would you say? Here it is. The Reimer-Tiemann reaction sticks a CHO group 1 to phenol right at the ortho spot using chloroform and a base. And the secret ingredient that makes it all happen? That crazy carbene intermediate. That's the entire story right there.
And that brings us to a final, bigger idea. What's so brilliant about this reaction is how it tames a beast. It creates this incredibly unstable thing, dichlorocarbene, and uses it to do something super precise. It just makes you wonder, right? What other fleeting, high-energy molecules are out there that chemists are using as secret weapons? What other tricks do we have up our sleeves?